Hello everyone, welcome back to my video. Today we are going to discuss about the topic called critical section. Let's get into the topic. Introduction to critical section. A critical section is a segment of code that must be executed only one process at a time. It is used to prevent race conditions and ensure data consistency in concurrent programming. Critical sections are typically protected by synchronization mechanisms such as locks or semaphores. Importance of critical section ensures that shared resources are accessed in a controlled and orderly manner, prevents conflicts and data corruption that can occur when multiple processes access the same resource simultaneously. Critical sections are essential for maintaining the integrity of shared data in multi-threaded applications. The critical section problem: n processes all competing to use some shared data. Each processor has a code segment called critical section in which the shared data is accessed. Problem: ensure that when one process is executing in its critical section, no other process is allowed to execute in its critical section. Implementing critical sections. Critical sections can be implemented using various synchronization primitives such as mutexes, semaphores, and monitors. Mutexes are commonly used for protecting critical sections in multi-threaded programs. Care must be taken to ensure that critical sections are short and efficient to minimize the impact on performance. Critical sections. We need to identify the code that manipulates the shared data. That code is called the critical section. Only one thread can be in the critical section at the same time. Use special entry and exit procedures to get in and out of the critical section. With this mind, with this in mind, let's fix the counter example. Deadlock in critical sections. Deadlock can occur when multiple processes are waiting for each other to release resources. To prevent deadlock, it is important to follow a strict protocol for acquiring and releasing locks in a consistent order. Deadlock detection and recovery mechanisms can also be implemented to handle deadlock situations. Starvation in critical sections. Starvation can occur when a process is unable to enter a critical section due to other processes constantly acquiring the lock. Fairness mechanisms such as priority scheduling or queue-based locking can help prevent starvation. It is important to design critical selections in a way that ensures all processes have a fair chance to access shared resources. Best practices for critical sections. Keep critical sections as short and simple as possible to minimize the risk of contention. Avoid holding locks for extended periods of time to prevent blocking all processes. Use lock-free data structures and algorithms whenever possible to reduce the reliance on traditional synchronization primitives. Performance considerations. Lock contention can lead to performance degradation in multi-threaded applications. Fine-grained locking can help reduce contention by partitioning shared resources into smaller units. Consider using read-write locks or optimistic concurrency control to improve performance in scenarios with high read-to-write ratios. Debugging and testing critical sections. Use tools such as thread analyzers and profilers to identify potential issues with critical sections. Write unit tests and stress tests to validate the correctness and performance of critical sections. Monitor systems metrics such as log contention rates and throughput to optimize the performance of critical sections. Real-world examples. Operating system use critical sections to protect access to shared kernel data structures. Database management systems employ critical sections to ensure data consistency and transaction isolation. Web servers use critical sections to manage concurrent requests and prevent data corruption in shared resources. Common pitfalls to avoid. Overusing locks can lead to excessive synchronization, overhead, and performance bottlenecks. Incorrectly implemented critical sections can result in race conditions and data corruption. Failing to release locks properly can cause deadlocks and resource leaks in multi-threaded applications. Scalability challenges. Scalability can be a challenge when multiple processes contend for access to the same critical section. Consider using lock-free algorithms or non-blocking synchronization techniques to improve scalability. Distributed systems may require additional mechanisms such as distributed locks or consensus protocols to coordinate access to shared resources. Security considerations. Critical sections must be protected against unauthorized access to prevent data breaches and unauthorized modifications. Use encryption and access control mechanisms to secure critical sections in sensitive applications. Regularly audit and monitor access to critical sections to detect and prevent security vulnerabilities. Evolution of critical section techniques. Traditional locking mechanisms have evolved to address the challenges of modern multi-core and distributed systems. Lock-free and wait-free algorithms provide alternative approaches to synchronization that can improve scalability and performance. Research in concurrent programming continues to explore new techniques for managing critical sections in complex computing environments. Case study, which is Java synchronized keyword. In Java, the synchronized keyword is used to create critical sections that are mutually exclusive. Synchronized methods or blocks ensure that only one thread can execute the protected code at a time. The synchronized keyword provides a simple and effective way to manage concurrency in Java applications. Case study, which is another case study, in Linux kernel spin locks. The Linux kernel uses spin locks to protect critical sections in the kernel code. Spin locks are busy waiting locks that spin until the locks is available, which can be efficient in low contention scenarios. Care must be taken to avoid holding spin locks for extended periods to prevent performance degradation. Conclusion. Critical sections are crucial for ensuring data consistency and preventing race conditions in concurrent programming. Effective synchronization mechanisms and best practices are essential for designing robust and efficient critical sections. By understanding the principles of critical sections, developers can create reliable and high performance multi-threaded applications. Thank you. Thank you for viewing this presentation on critical sections. We hope you have gained valuable insights into the importance and best practices of managing critical sections in concurrent programming. Have a great day. Thank you.